Oh, no gong yet. Jessica, are we good to go? No, she gets to gong during the.
We gotta start people up.
Well, I'll give you a. All right, so I think we're gonna get started. This is a really great seminar where we have some high school students from the Valley that are here. We have some prospective graduate students that are here visiting. And this is a really fun seminar where you guys get to learn about a lot of our different research. We couldn't fit everybody, but we have a big mass of faculty that are presenting some of their research and things about the department. But the way this is structured is we all are going to have 3 minutes, and we will not go over 3 minutes, is because Linda will let us know. Linda is really good at gonging. So you can congratulate her after the seminar. Oh, we have more coming. Great. I'll wait for just a second and maybe restate things. Okay, well, thank you for joining. This is our weekly material science and engineering seminar. Like I already said, I'm excited for this one because you get to see from a lot of different faculty of the research that we're doing. We all have 3 minutes exactly, no more. And Sierra's going to help us with the slides, and we're going to get started with rules. There's 10 presentations. We only get 3 minutes. There's only one slide, which I'll show you how to get around that when I go. And after 3 minutes, you'll get the gong from Linda, which is still that one. Okay, so our first speaker today is Dr. Eric Jankowski. He's our fearless leader for the material science program. And go.
Thanks, Brian. So in my lab, the Computational Materials Engineering Lab here at Boise State University, we make flat things made out of carbon. So did you know that you can make a solar panel out of plastics? This is an organic solar cell. You can roll it up. You can charge your phone with it when you're camping. We can pass it around so you can have a look at it. And that solar panel is made from polymers, where the structure of the polymers, the arrangement of the building blocks and the overlap between their pi orbitals gives it the electronic properties that are sufficient for catching light, turning it into electrons that flow through a circuit that can then charge your phone. And it depends upon the structure of those polymers on the microscopic level, on the molecular level, and the microscopic level. So if you zoom into one of these solar panels, you've got this phase separated structure. And depending upon the amount of the interface between the molecules that catch the light and then the molecules that take those electrons, you have higher or lower efficiency. So the efficiency and the ability of one of these solar panels to charge your phone depends upon how we structure those molecules. So we choose the shapes and the interactions between those molecules to give us the structure that we want. We also do that with airplanes. These are also made out of flat things, made out of carbon. So if you take unidirectional carbon fibers and you impregnate them with similar plastics, similar polymers that are in these solar cells, you get these tapes. These tapes you can lay out into different shapes and make the wing of an airplane. This is the carbon fiber composite wing of a Boeing 787. It flexes when you take off. It gives you a smoother ride than the aluminum wings on the previous models. And you can make these pieces. You can weld together the pieces of an airplane wing like this, and the interface between those different pieces depends upon the structure of the polymers that make up that weld. And so in our lab, we perform these molecular simulations where we look at how the chains entangle across the interface and then pull on those interfaces. We do these tensile tests to measure the mechanical properties of these welds. And so we try to understand, how can we make better aircraft faster, cheaper, lighter, so that they're more efficient? We can manufacture them safer and at scale with lower costs. And the same science goes into the manufacturing of solar panels that are made from really, really similar materials. And we do this with some of the biggest supercomputers on the planet. So the students in my lab spend most of their time tippy-tapping at a keyboard, learning how to write code in Python and develop these computer simulations. And that's everything that we do. That's it. That's the whole thing.
Thank you, Dr. Jankowski. And I didn't point out earlier, but we're going to save all the questions for the end. So write them down. And then at the end, we'll have an opportunity to ask all of us questions. So are you ready? All right. So our next presenter is Dr. Peter Milner, and he'll be talking about his toilet paper.
What is a meaningful career? Do you have purpose that drives your career decisions? I believe that engineers with a purpose have more satisfying careers and their careers are more impactful. Purpose is something that connects my innermost beliefs, my values, with the outer world. The big picture is important, and that is why I promote big picture thinking in my classes. Here's an example: toilet paper. Do you remember March 2020, standing in line for toilet paper? New York City has a flush hour. Toilet paper demands infrastructure. The environment. In the 1990s, colorful toilet paper caused problems for water treatment plants. Global toilet paper production consumes 27,000 trees daily. Properties. In 1930s, an advertisement hailed their products as splinter-free. Toilet paper is soft, yet non-clogging, strong, yet biodegradable. That's engineering, an engineering feat. Priorities. In the 1970s, I visited my granduncle who had no toilet paper. Instead, I found a stack of newspaper squares on a shelf. Why pay for something for which I can actually use my old newspaper? There was a time before toilet paper was mass-produced. Printing of newspapers nurtured the cause. In America, toilet paper was invented in the middle of the 19th century. At that time, the mechanization of agriculture caused mass migration to cities. Steel was mass-produced and high-rises appeared in Chicago and New York City. That's when the flush toilet was born. No high-rise without flush toilet, and here comes toilet paper. Necessity is the mother of invention. Inventions change how we live our lives, and the way we live impacts the world. Only those inventions that respond to the necessities of our time change the world. Without engineers with purpose, who will tackle the grand challenges? The big picture turns into a purpose when I respond to the needs of the world in accordance with my beliefs. That is why I bring the big picture into my classroom and make it part of my scholarship. Solving the big issues of our time requires engineering graduates that have a sense of purpose. Do you have purpose? Thank you.
Thank you, Dr. Mullen. That was great perspective. And many of you maybe didn't think quite that deep into it, but that's great that we get to engineer what? Okay. All right. So the next presenter is Dr. Caitlin. I think Caitlin.
Either one's fine.
Either one. She
Yeah.
likes both. Duncan from the DNA Research Group. So when you're ready, go.
Hey, hi, my name is Katie Duncan. I'm a postdoctoral research fellow in the quantum DNA group. I joined about 3 years ago after getting my PhD in chemistry from Montana State. The quantum DNA group is comprised of about 30 plus students, faculty, and staff. The students play a really large role in our group. We've had high school students, undergraduates, and grad students do some really great research. Our group is divided into 5 different teams with specialties in simulation or synthesis, characterization, and theory of molecular modeling. And our collective focus is on quantum information systems. So in 1999, Nakamura and his group brought forth what's called the Josephson junction. This Josephson junction is 2 superconductors that are held together or separated by a thin insulating layer. And these Josephson junctions can host gigahertz frequency superpositions, which is that squiggly line you see up there. To think of a superposition, you can think of coins. So a coin has 2 states, heads or tails. A superposition would be a spinning coin, or a third option where it's not clear if it's heads or tails. These Josephson junctions are currently being used by IBM, Intel, Microsoft, Google for quantum computers, but they have a really big downside. They operate at millikelvin temperatures, so that's 2 orders of magnitude colder than the temperature of space. So there's a big push in the field right now to overcome this low temperature limit. And we believe we're working on a way to do that. So we use molecular aggregates brought together using DNA as a breadboard to host these quantum superpositions. When these molecules are brought together, they can share their excitation energy. And when the packing arrangement of these molecules is just right, we can get 2 allowed electronic transitions. And that's seen in the absorption spectra, where you have a peak at higher and lower energy than the monomer. And these molecular aggregates can host or have higher frequencies, and therefore have the opportunity for higher operating temperatures. One downside to these is they operate at a femtosecond timescale. So you need instrumentation that also is on that same timescale. So in our lab, we use ultrafast spectroscopy to do this. We've leveraged the expertise of Dr. Daniel Turner and PhD grad student Nick Wright to build a one-of-a-kind instrumentation that's capable of doing this. So together with the quantum DNA group as a whole, we're hoping to do what Nakamura did in 1999, and hopefully in 25 years from now, we can see molecular aggregate-based quantum information systems.
All right, thank you. That's to Corey.
Real pressure getting this on.
That really wants to.
The gong is happening in about 3.5 minutes. I guarantee it. Do we have a laser pointer?
Sorry, Zoomers, I'm gonna be all over. You're not gonna see anything I'm pointing at.
Okay, are you ready?
Sure.
All right, go.
All right. Hey, everyone, I'm Corey Ifa. I'm part of the Surface Science Lab at Boise State University. And we at the Surface Science Lab exist within the middle of this tetrahedron that material science and engineering is all based upon, all the principles of it's based upon. And we do characterization to obtain properties of different types of materials. So let's say you change the structure, you change how you process the material. We're going to figure out what are the properties of that, which in turn impacts the performance of how that material is going to behave in a certain application that you're utilizing. We do this by utilizing atomic force microscopy to characterize material properties at the nanoscale. And so when I say the nanoscale, I'm talking insanely small, 10,000 times smaller than the width of a human hair. And we do this to observe things that we cannot see with traditional methods like an optical microscope, to see structures such as some quantum DNA stuff that Caitlin was talking about that we can turn into an origami shape in the shape of the Boise State B logo. And we can see that at this ultra small scale. We do this with an ultra resolved probe at the very tip of this, few atoms in its width, to be able to trace our topography as well as other properties of all sorts of different kinds of materials. Got a lot of examples here. We can look at the topography, just simply how rough is your sample. You can look at how does a thing disperse onto the surface of a material, such as this, oh my gosh, I already forgot what it's called. Self-assembling diblock copolymer. Yeah, who knows what that is? We have electrical modes. We can observe current as a function of an applied bias through some type of device. Or in the case what we're looking at here, we're looking at a 3D printed titanium alloy and how the surface potential is distributed amongst that, and can correlate that, in fact, to different types of characterizations, such as electron microscopy, so we can further our properties versus structure correlations. And this ultimately provides a driving force for what we end up seeing as corrosion in real life. We can look at magnetic properties. So this is a 3-dimensional overlay of the magnetic phase on top of topography. We get these interesting little dipoles. So basically, this is a, I already forgot what this one's called too. It is a lattice that is a, oh, what is it called? It's an artificial spin ice lattice. And this is basically, just simply put, a bunch of tiny little micro magnets that stick together, and it allows us to store, based upon this switch of these poles, these dipoles that we have, now suddenly we can store information with that. We can poke a bunch of different types of things. We can take a diamond probe and we just poke and we indent on metals or ceramics to get an understanding of how it's going to behave. Or we can poke on biological things such as cells, and we can understand its response to that mechanical stimulus. We can also poke it hard enough to eventually see how much force does it take to rupture a cell. Or we can scratch on a metal or a ceramic or a coating to see what's its wear resistance. We can take a battery, we remove it from air and water, we put it into an electrolyte inside a glove box. Nice little picture right up here to show that. Yeah, nailed it. Oh,
Thank you, Corey. I'm glad you fulfilled Linda's dream of calling somebody. Felt good. She's happy. Just gonna remember it.
Kind of. Okay, let me see if I can click on here.
That was good, Corey. We're all excited for the next.
It's give me
So-
pressure,
What's that?
to give me stress,
Did you stretch? He
pressure.
was the first one to get going. Okay.
Okay.
All right. So now we'll talk, we'll have a presentation by Dr. Lon Lee from the Materials Theory and Modeling Group.
Okay, let's see. Okay, great. And thank you, Corey, and then Katie give a fantastic introduction. So my group what's doing is like before you head to Corey or Katie's labs, and then you want to know what really happened, what you expect to know, right? Will not burn your cell or kill your cell or toxic your cell. So that's why we need the computational modeling. So that's what my group doing. And so I put the grand challenge here because everybody love grand challenge nowadays. And also how can we save the world, right? Well, the grand challenge is like, how can we solve the room temperature quantum computer problems? And because nowadays, like Katie said, the quantum computer is require very low temperature, nearly 0 Kelvin, and also very large, like a footprint sprint, and also require very low humidity. And then but it's not feasible. If you want to have a quantum computer, right, quantum computer chips in your cell phone is far away from that. So that's what our group try to do is like, how can we solve those grand challenge? And what we do, we leverage, of course, interdisciplinary collaborative effort, including AI, machine learning, that's our friend now, and then data science, computational material science, organic chemistry, DNA, nanotechnology, of course, are integrated with the experiment like the Katie's group and also Corey's groups. And what we try to do here, this is the quantum computer we try to build. We already have the proof of concept that will work. So you say, totally, what is that black dots? Okay, each black dot you can think about that is organic chemical molecules, and then which can absorb and emit light. And we give it the name called dye. So not the dye you dye your hair, okay? So we give it the names called dye or dye molecules. And if we can arrange those dye molecule in such a beautiful configuration of beautiful structure, and then actually the dye can implement the computations and can also transport some quantum particle we call the exciton, and from the left side and to the right side without any energy loss. So it'll be fantastic. Even we can make this and put it into your cell phone. Your cell phone will not get overheated, and you can use it, and you can save the battery. The battery can go like forever, something, because it's a no energy lost. But you ask me, totally, how can we control the dyes, right? In the certain configuration we want, we use the DNA. So here, this is some of the simulation my group is trying to do is a DNA duplex, and then we can attach like 2 dyes and at the backbone of the DNA. And then we also currently try to make this like a dye, we call it dye aggregate or dye very, very long as we want, and to build such structures. So if you're interested and want to know more about that, and feel free and then email me or stop by my office. Thank you.
All right. Thank you, Dr. Lee. All right. So I'm excited to welcome Dr. Dimitri Tene from the physics department, and take it away.
Thank you for introduction. I'm Dmitry Tene. I represent the Department of Physics here. So my research deals with optical spectroscopy of a variety of materials, which can broadly classified as multifunctional oxides and semiconductor nanomaterials. So our complex oxides is a very vast family of materials which can have a wide variety of properties. As a result, we can have huge number of potential device applications for them. Specifically, my research deals with materials called perovskite oxides, and schematically the structure is shown here, which would have oxygen, those red atoms, and a couple of metallic ions in the corners of that cube. And my research focuses on what's called ferroelectric and multiferroic, which are spontaneously polarized and magnetized materials. And we deal with artificially engineered nanostructures. Corey already told you what nanoscale is, and that is a very small scale, and we deal with very thin films or superlattices, which is layered structures of different materials, like what is shown here on this picture of electron microscopy. And having these artificially engineered materials allows to manipulate their properties to achieve better device performance. The samples like this are synthesized in the laboratories of my collaborators, and then we do characterization, including the facilities of Boise State Center for Material Characterization. Our part is optical spectroscopy, which means we shine light, which is known. We know what comes out of our laser. And then we collect light which comes out of the material. It can be fluorescence or photoluminescence. You observe that every time you drive your car at night, when you shine your headlights on road signs, they fluoresce. Another type of data we get is called spectroscopy, light scattering spectroscopy, which is what you see, that green dot there is scattered light. But there is also a little amount of light which scatters a different color, different wavelengths. And that is what we analyze using this high-resolution tool we have in our lab, and that is what is called Raman spectroscopy. And what kind of light it is reflects the properties of the materials we study. So that is pretty much it. Sorry for not making the gong. All right. All right.
All right, thank you, Dr. Tene. Gonna get gonged? That gong? No?
Hope not.
I hope not. I hope you do. Then I won't feel as bad.
Hello?
Yeah, look, I mean, Lon's already went, Peter, like, we're doing good.
Student shows you up in the fall.
That the students are generally better than us. That's fine. Okay, so I'd like to welcome Dr. Daikong Da from the Mechanical and Biomedical Engineering Department, and go.
Oh my God. I think I have some slides, just show that one by one, not enough for time. But it's okay. Okay, before the slides, let me do experiment and ask you one question. So what if we have a crack in the middle of this paper and we pull on both sides? The crack will be propagating from the initial crack tip, right? But what if I told you, and I dig in some holes in this paper, and then I do the same thing to pull this paper, but it takes you larger force and it takes you longer to break the paper. Is that cool? Very cool, right? But we're not doing paper engineering. We're doing mechanical engineering in my department. So how many of you watched the Titanic, the movie? That's good, right? When the Titanic hits the iceberg, that's a crack. So that's the TIF there. So when the Titanic hits the iceberg, there's a crack, the water comes in, the head of the boat will becoming heavy, and then it's gonna sink, and thereafter, there will be a huge stress in the middle of the boat, and then there will be a new fracture in the middle of the boat, and then the boat will be totally sunk. So now what if we can make the time between that the boat hits the iceberg and then before the boat totally sinks? If we make that time longer, so we can save more people's life, right? That's cool. And my final question today, what does that picture remind you of on the top right? A wall. Why the wall has that architecture? And I did a simulation that once you have a wall like that, if you have a crack, the final crack would be zigzag instead of like immediately in a class like a catastrophic failure, you have some zigzag to prevent it to be clear quickly. So you can have more time to escape if there's a disaster, okay? So that's what I'm doing. So in the aerospace engineering, once we finish the modeling, forward modeling, then you need to do some inverse design such that you can dig in some holes in that airplane wings ribs, right? That is exactly the architecture right now. The aerospace engineering is building you aerospace wing ribs, okay? But sometimes you don't want to digging holes, right? You want to keep the overall shape. That's why you can digging holes at very small scale. This is a mesoscopic scale for some engineering connecting rods, but you can even digging holes on very small microstructure scale and atomic scale, right? And this picture is that once you do forward simulation, reverse engineering, you want to do manufacturing to validating your model, to validating your design. Okay, that's it.
All right,
No, I cannot finish.
it's me. Yeah. Yeah, I'll introduce myself. Wait till it changes. You can't cheat me on my time. Okay, I don't want to get gonged. Okay, hello, my name is Brian Jaquis, and I'm in the Material Science and Engineering Department. I'm the director of the Advanced Materials Lab here, and where we are making materials that matter. Our diverse research group is comprised of undergrad students, postdoctoral students, research associates, and even high school interns. We're a very collaborative research group, and we work not only with other groups here on campus. In fact, lots of the presentation you've already seen are things that we've participated and collaborated on, but also around the country, different national labs, different universities, and internationally with the University of Manchester. So we generally are researching materials for extreme environments and nuclear energy applications or technologies. And when I say extreme environments, we're essentially pushing the traditional limits of materials by bridging the gap between fundamental science and applied engineering. So you've already seen this, what we call our material science tetrahedron, which Corey presented earlier. And we do it, so we're using a similar, but we're encompassing this tetrahedron where we're building new materials and studying the relationships between the processing structure, properties, and performance through various characterization and testing. Did you know that there's 760 million people across the world that don't have access to electricity and 2.8 or 2.1 billion people that have water scarcity? So one thing we can do to help with this is provide more energy and make it more available while working on keeping our net zero, our carbon footprint low. And we do that with nuclear energy. So you may or may not have seen something like this, which is just a couple cooling towers from a nuclear reactor. And this is one of the most extreme environments that you can put a material into. So what is a nuclear reactor? Well, essentially, it's a really fancy and expensive way to boil water. You boil the water, it spins a steam turbine, the steam turbine spins and creates electricity, and then you have electricity for the grid. So they operate at high temperatures, high pressures, and can be surrounded by corrosive environments, not to mention all of the ionizing radiation from the radioactive materials. And those those radiation, they kind of move the atoms out of their happy place, right? And cause some sort of disorder or entropy, which causes the materials to change and their behavior changes. And so the initial design has to be modified. So one of the challenges here is the time it takes to innovate in this environment, because it's costly and time prohibitive to innovate in a nuclear reactor environment. So my lab focuses on novel solutions to make nuclear reactors or construct reactors or make innovation in nuclear faster and more efficient and make it more accessible to remote areas. And one way we do that is through additive manufacturing. So you've probably seen something like this before, where you heat up a polymer and you extrude it in certain locations and you 3D print, right? You probably have all done this. Well, we do it with metals. So I have props because I cheated. So we have cool metals that we can make. And here's two different examples where this is a laser powder. Seriously? Oops. Oh, you're doing it. I'm doing it. I think you cheated me. I practiced. That was worse than last year. That was terrible. You pushed the button too soon. I know it.
That's funny.
Well, I guess me and Corey we got this nailed down to be on time.
Okay.
Okay. So it's my pleasure to introduce our next speaker, with Dr. Claire Zhang on the batteries and electrochemical energy materials lab. So take it away.
Okay, thanks, Brian. Oh. Okay, so my lab, as the name says, is an electrochemical energy materials laboratory. So in our lab, we are basically trying to either use the electrochemical method or use the materials for electrochemical reactions. So one of the kind of a core area that we are working on is on the batteries. So you probably all know that we now cannot live without battery. Even my son is always using a pad every day. So currently, no, you are not using. So currently, most of the portable electronics are all like for large scale energy storage is powered by lithium-ion batteries. But in the past few years, we see a lot of issues, especially with supply chain challenges, that we want to reduce our dependence on the lithium or cobalt, which is heavily used for lithium-ion batteries. So in our group, we are trying to develop a sustainable battery system, which is to use sodium. So you can use your kitchen salt to make the batteries. That's our ideal. And then so we can also use it for different applications, for renewable energy, to make it more resilient in terms of the how you can provide the energy when you can store the energy, and you can also use it for the portable electronics and also for electric vehicles. But there's a lot of challenges associated with this new chemistry. Even though the sodium chemistry is similar to lithium chemistry, but we also see a lot of challenge, because if we want to provide you with the same customer experience, we need to provide a similar energy density. But currently, in theory, the sodium-ion battery will provide a lower energy density compared to lithium. So we want to develop the new materials that can provide higher energy. But then we also face challenges, like you see, you will have a lot of like reactions with the electrolyte that will cause the degradation. And then you also undergo more of the structural change compared to the lithium system. So this is what my lab is working on, is trying to manipulate the structure so we can stabilize both the interface of the materials within the bulk structure, and also at the interface between the electrode and the electrolyte. And so we can provide the comparable performance of the current leading lithium-ion battery technologies. Okay. One time, right?
Way to be on time. Really proud of everybody here.
One last so I can keep going.
That's right.
Oh, yeah, they really want to gong me, I've been told.
Only one. All right. So now we're gonna hear from Dr. Josh Eisenberger in the Eisenberger Research Group.
All right, here we go. All right, so first thing I want to highlight is the research my group does is all based on nanomaterials. And as we heard from Corey, just to bring that down to scale, nanomaterials are defined as a material less than 100 nanometers in at least one direction, one direction. So the reason this is important is because when you make a material at the nanoscale, you fundamentally change a lot of the properties of the material. One way to highlight this is when you make a nanomaterial, let's say 10 nanometers, a large fraction of your atoms on the material are then on the surface. And what that does is that fundamentally changes a lot of the properties of materials that we know. So my group, what we do is we try to synthesize nanomaterials through a lot of different methods. We do wet chemical methods where we mix them up in different solutions, try to pull different levers, push different buttons, change the properties. So we characterize them, and then we do this feedback loop where we synthesize them, we change conditions, and then we characterize them to see how we're modulating these properties. After we've modulated these properties, we can then apply them to a lot of different areas. So one of the areas we look at doing is advanced manufacturing microelectronics, where we'll deposit these materials on wafer for stuff like memory, like at Micron, or we do printed electronics, where we take these nanomaterials, we suspend them, we make inks out of them, and then you take them to these printers that operate on a lot of the same principles as like your office, your at-home printer, but we can print them on a lot of different substrates, flexible, so you can make wearable electronics. We test them like with Brian in different extreme environments, develop strategies to get them to survive in space, like making shielding coatings. And another area that we work in is the biomedical area.
So we can take these materials because they're so small, they're now on the same scale as a lot of your biomolecules like DNA. And then because of these interactions at the small scale, they interact with your cells in different things in unique ways. So what I'm showing here in this area is a new drug delivery strategy that developed in the research where you take these nanomaterials, you encapsulate them in a lipid membrane, which is your cell membrane, and then you can irradiate them. If you encapsulate like chemotherapeutic drugs for cancer delivery, what this does is that effectively makes them non-toxic to the body, so you can inject a patient with them, let it all accumulate in the tumor, and then after they've accumulated, you can irradiate it, which causes it to release the drugs in that localized area, hopefully reducing all the side effects that chemotherapeutics cause. So we take these nanomaterials, we synthesize them, we characterize them, and we apply them. Thank you. Ready to get gonged. Huh? Stay down. Oh, stay down. Woo, I went fast. What was I at?
Seconds left.
Sweet.
Those should
That's
have been
right.
my 20 seconds.
You can have them back, Brian. Go ahead and finish.
So I'd like to invite the speakers down. That was our last presentation for today. But I want to offer for any audience questions. Is there anybody that has any questions for any of the speakers today? Ajay.
Can I go? Yeah, I have a question for Dr. Muller. In today's situation, what is the big picture we want to see, or we can see, or we can project for our generations, few generations?
So is the question, what are big pictures or big?
What are the big pictures in current situation of political or mining or anything?
Okay,
We should focus on.
What qualifies as a grand challenge?
Yeah, exactly.
Okay, and we have seen a lot of grand challenges here in different senses that we have seen. Well, making a quantum DNA computer is a big task. What I think about grand challenges, I think about what, for instance, I've seen a couple. Dr. Chong brought some in, and also who else? I think Dr. Jacques talked about water scarcity worldwide. 2 billion people have not enough water to drink. That is a grand challenge that's out there that cannot be solved with making a technology. Or supply chain issues that we have, which we want to make our wind turbines, and there are magnets in there, and those require materials that we dig out of the ground somewhere where there are slaves going into the ground and children are buried alive. These are big problems that we cannot solve with single policies. We cannot solve with a technology that we cannot solve with sitting in a classroom or in a think tank and just come up with a solution on the board. And we don't know when are we done. And so also there is the term wicked problems out there. Housing crises. How do we solve a housing crisis? And that's what I think about is when I think about an outside problem that is not my technology. It's not my pet peeve or my whatever I like to do as a hobby, right? But it is something that's out there that really is bigger than myself. It comes from the outside, and I would like to contribute to. That's what I think of a grand challenge. And then I come in and say, well, who am I? And what do I do? What do I like to do? And how can I contribute to that grand challenge and make decisions about my career that lead me to a job or whatever, an office or whatever it is that helps with that big thing.
Thank you, Dr. Muller. Any other questions? I'd like to encourage some of our guests to ask questions. We have a question over here.
I have a question for the person who was talking about the toilet paper. I I was just wondering if toilet paper was like your favorite, like either like research or like thing to like talk about.
Well, we like to use toilet paper, don't we? And have a hard time imagining a world without. But actually, there has been toilet paper has not been around for always, and that is one thing that we realize when technology that we use, we might take it for granted. It might be everywhere, right? And we don't think about it, but it came to being at some point in response to a need and in response to some drivers that society provides. And we are often not aware of those, but there is a paper by a name escapes me, late 19th century, and it is called Acres of Diamonds. A person says, well, I identify a need in the world. If I want to become rich, identify a need, and then apply yourself to meet that need, and all the rest will take care of itself. Okay, so I think asking for those needs, that's what I think that I promote.
Thanks, Dr. Muller. Oh, got a question. Hopefully the next question's over on that side.
If I were in high school, why should I come study material science at Boise State?
Do you ask?
Eric?
You should come here because we have nice faculty, world-class resources, the ability to grow these thin films, to characterize these thin films, to simulate all of these different materials that you've seen today, to probe these femtosecond transitions in quantum materials. These are world-class facilities that don't exist at other places. And they're right here in Boise. And you've got access to employers like Micron, Photronics, Idaho National Lab. I was telling some of the high schoolers downstairs earlier, but half of you didn't hear this, that every battery, battery on a NASA probe. So these are Mars Perseverance rover, Mars Curiosity rover, Voyager 1, Voyager 2. Every probe that NASA has sent into space has a battery pack that's a nuclear reactor that's made by hand here in Idaho by material scientists. This is why you should come to material science here at Boise State. And when you graduate, you'll get a job making on the order of $100,000 a year. That is generation-changing income. What are the downsides?
But wait, if I'm only a freshman or in college, will I get to do any of that stuff?
Absolutely. We need you to do all of this stuff. All of our undergraduates finish up with some kind of experiential learning, whether it's working in a lab, interning at Idaho National Lab or Micron. It's required. Oh, Corey.
We have 4 undergrads that work in just our lab. That's like how everything runs in our lab. It's undergrads, and I also was an undergrad, and now I'm not at the $100,000 a year, but I'm aspiring to be. And also notably, tuition is obscenely cheap here. I went somewhere else out of state to start off with, and I was like, I'm gonna go broke. I came back, I got a great education. It was dirt cheap comparatively. So your parents will love that too. So yeah.
Did you have a question? Oh, okay. You have a comment? Okay, let's hear it.
As someone who's retired from this industry, I can give you 2 pieces of why materials and processes, and then why Boise State from my very limited observation. The first one is, you want to make anything, clothes, tables, buildings, satellites, rockets, which is my background, batteries, anything, you have to understand materials and processes. Most of my background has been in, I'll call it the non-nano molecules. It's in the stuff you can touch and feel. What Boise State brings to this is all the way from the atoms on up, and it's integrated for a purpose. So those are my 2 things. Materials and processes, you go to the hardware store, what paint do you want? You go to Boise State and you say, what are the electrons underneath the paint I'm going to buy?
Great, thank you.
My question's for Dr. Eisenberger. What's your favorite nanomaterial and why?
Favorite nanomaterial? That changes. It really depends on the application. Recently, my favorite one to play with is gold, because one, we can make it at such a small scale. It's only a couple nanometers and it has these really cool features. I won't go into details, but it changes color based on the size you make it. So that one, you can have it at like a dark red purple color, all the way to like a blue-green color, depending on the size of the nanomaterial. And it's very chemically inert, but it's highly conductive. And we can actually get this gold to melt at really low temperatures because it's made in nanoscale. So that's a really cool one. If you go back to me like 5 years ago, I'd have to say zinc oxide was my first material love because it's what I did in grad school. Has a lot of cool properties, and again, it's biologically inert. It's recognized as generally recognized as safe substance from the FDA, but we can use it for cancer research. It's actually more toxic to cancer cells and healthy cells, better than a lot of your chemotherapeutics. So I really can't say I can pick I'll just say nanomaterials are my favorite, just because they have a lot of cool properties, a lot of things to discover.
She's booing you.
Boo. What's your favorite?
Maybe it used to be graphene, but at this point, I think it might be titanium carbide Maximus.
Titanium, yeah.
Other questions?
I have a question for whoever was talking about essentially the particles that never lose energy. How does that, like, I'm confused, like, do they just lose energy at a very slow rate, or do they never lose their energy?
I think that was that for you, Dr. Lee?
So yeah, I mentioned that. Yeah, so it's not particle. We call it quantum. Yeah, quantum particle. Something we call like exciton. So probably some of you, if you already have like general physics, and then so when you excite, like you try the lines on any molecule, and then so the electrons, and on the ground state, we excite it to the excited state, and then we'll leave a hole on the ground state, and so the pair of the hole and the electron pair we call the exciton. So what those molecule try to transport is the exciton transport, and then we found that from the theory. So if Bill could approve me, right? And we haven't really detected yet, but from the quantum theory, we proved that the exciton can be transported and through those molecules without any energy lost. So most of the time you see like why we call, hey, we care about energy loss is like, for example, now your cell phone, right, always overheated. It because the electron transport, and then the electron transport will lose the energy and through the heat. So that is why we fascinating about this system. Yeah.
This question's for Dr. Jankowski. You were talking about the sizes. A lot of you, a common theme that we have here is the shrinking of the structures for functionality. Two double-barreled. One, are you finding limitations with Moore's law in being able to scale down structures? And my second question would be how historically we use immersion photolithography to print like current structures. So what new technologies are being developed to achieve these smaller structures?
Yeah, these are great questions. So with the plastic semiconductors that we work on in my lab, we're talking about length scales much larger than some of the like 5 nanometer circuit elements that are in silicon-based semiconductors today. So we're not running into those same kinds of problems. It's actually kind of an overlap with what Lon was just talking about. So exciton transport is one of the things that matters the most for like the organic solar cells and the conductivity in the thermal conductivity in those composites made from plastics and carbon fibers. So we don't have the same kinds of Moore's scaling challenges there. But what challenges we have is the really messy building blocks like polymers that get all tangled up with each other, controlling that entanglement in a way that gives you mechanical strength, but where you can exploit maybe some short range ordering to get the thermal properties that you want. Those things are really challenging. And that's where our computer simulations give us some insight is we can realize, wow, if you've got like some really short chains and some really long chains, we can make these bonds very quickly that are very strong. And these are the sorts of design rules that we can give to our folks that are at like Joby Aviation, where they're trying to zip together larger structures from smaller and smaller parts. So that's the sort of the kind of the way that we think about that. Did that help answer your question? Great. I have a question. Who's got my solar panel? Cool. Thanks, Sarah.
I have a question
Some
to
of us
Dr.
have
Eisenberger.
different places here shortly. I think we're going to cut off questions. I know there's one online, and maybe we can address that if at a later time. It was for Dr. Eisenberger, but let's thank our speakers. I hope you all enjoyed it. We had fun doing it, even if I got gonged way early. Jessica has directions.